Welcome to Aryabhat Center for Theoretical Physics. This is the sixth lecture on this lecture series called Electromagnetic Theory, and from this lecture I am going to fully explore what you call mathematical formulation of electromagnetic theory. So I will begin with the definition of field. So what's a field? Field is a function which describes a physical quantity at every point in space. If we imagine that in this space there is a infinite number of points near to each other, then a field we can assign each point as a function fxy. Suppose this is y and x, and this fxy describe a physical quantity at each point in space, and that physical quantity can be everything. It can be anything. It can be temperature, it can be energy. So field is actually a function, and it can be one dimensional, it can be two dimensional, or it can be four dimensional, or it can be three dimensional. So in relativistic theory we have four dimensional function. So field are two types. One is called scalar field, another one is called vector field. We know that there is a scalar and there is a vector. Scalar only has a magnitude, but vector has magnitude and direction both. So in that sense, scalar field has only value. So scalar field is also a function which assign a unique scalar to every point in any given region. So at each point there can be a function which assign a scalar quantity to each point, and that scalar quantity can be a scalar. So f equal to fxyz, fxyz, this can be a scalar function. And best example of scalar function in one dimension is gravitational potential energy. Suppose this is the earth surface, xy plane earth surface, and this is the z which is perpendicular to this xy plane. Then gravitational potential energy we defined as mgz, and we can see that the gravitational potential energy phi only depends on the height from the earth surface. So it is the best example of one dimensional scalar field, gravitational potential energy. Same way we have two dimensional scalar field which is called temperature. This is the plate, and in this plate in some region there is a much cooler temperature, there is much hotter temperature. So this temperature of this plate can be described by Txy is equal to 250 divided by x square plus y square plus 1, and you can see that it is a two-dimensional scalar field. Remember, temperature is a scalar field, and we can describe by x and y. So temperature can be described, temperature as a scalar field can be described by two dimension, x and y. It can also be described by three dimension, but temperature we can see that it is the best example of two dimension scalar field. And three dimension scalar field is electric potential, where V is the electric potential equal to 1 by 4 pi epsilon naught q by r, and r is root x square plus y square plus z square. So it is the three dimension scalar field. Best example of three dimension scalar field is electric potential. Now how we represent scalar field? So we represent scalar field by contour, curves or surface. Imagine you are climbing a mount, any mount, and you reach certain height from the surface. Now draw a line parallel to your point like this, and you can see that this line which goes across the mountain is called contour curves. We can draw many number of contour curves on this mountain which is at the different height. So this person is at A, and again there is another person which is on different contour curves B, this is C, and you can see that if fxy is the contour curve, then at each curve fxy is constant. It means value of scalar field at this contour curve is constant. And one thing more, if curves is much closer than each other, it means scalar field is changing rapidly, and if contour curves is far away from each other, it means scalar field is changing slowly. And remember, at each contour curve scalar field is constant. It means value of scalar field is constant, and this is the example of contour curve on the plate. At each plate you can see that at each contour curve you can see that there is a different temperature. Here T is suppose 100 Kelvin, at this line T is 140 Kelvin, this etc. So this is the best example of contour curve, and we represent scalar field by contour curve or contour surface, unlike the vector field where we represent this by what you call lines. So this is the brief definition and representation of scalar field. Now in the next video we will learn how scalar field changes with time, or when change degree of change take place at each point, how we can define scalar field.